Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. Today, we'll be speaking with Brian Morin, CEO of Soteria Battery Innovation Group. Soteria has been developing a current collector and separator system that should make conventional liquid electrolyte batteries non-flammable. And with that, I'd like to welcome Brian. Thanks for joining us, Brian.
Yeah, thank you, Jordan. It's good to be here.
My first question is, what is Soteria? Is it a consortium or a company, or is it a consortium that formed a company?
So it's actually a company that formed a consortium. What we found is that big companies don't want to put a startup as a supplier for a critical material for their main products. They'd rather have big companies. So I looked the world over for a business model where you could take a technology broadly to an industry. And we found the Bluetooth business model. Nobody knows that Bluetooth is a consortium of 35,000 companies who own a technology and licensed it to about 30 chip manufacturers, and then who then sell the chips back to those 35,000 companies. So we've copied the Bluetooth business model and are using that to take our technology into the battery industry.
That's excellent. It's actually a really salient point, because one thing that's happening at the moment is there's an electrolyte additive for batteries. And I think the patent is owned by one company. Maybe it's Mitsubishi or something like that. But they're able to charge through the nose for that additive, and companies, it's not the best situation for the companies that are buying that additive, because then they're basically at the mercy of one individual or one company. What was the genesis for the technology? That is, where did the idea for this all start, for the current collector and separator?
Yeah, so the separator, actually, the genesis for it was about 10 years ago. I was leaving my first startup, and a friend of mine asked me, said, "What are you going to do now?" And I said, "Well, it's 2010. It's easier to make a job than to find one." And he said the magic words: "Have you ever thought about making a battery separator from a nanofiber?" And I was quickly Googling both of those words because I didn't know what they meant. But he and I co-founded a company, Dreamweaver, to develop the separator. And we did everything right except two things. The two things we did wrong is we tried to make it and sell it ourselves. We tried to insert ourselves into the supply chain of Panasonic, Samsung, Sanyo, who really want big companies, not small companies, in their supply chain. And then the other thing is it was only part of the solution. It thermally stabilizes the battery, but if you have a damaged spot, it doesn't stop the flow of energy to that spot. So you could still light the electrolyte on fire if you had enough damage in a big enough battery. So that was where we sought to find a way to fix that, and the current collector was the solution that we chose to stop the flow of energy into that spot. And that was about 2017. So it took me 7 years to figure out our two mistakes. I'm a slow learner.
These things take time. As they say in a lot of startups, it's the key thing is the people in those startups, and they can find solutions to problems. It's just a matter of time if you get the right group of people together in the right minds.
It's an overnight success, 10 years in the making.
Yeah, exactly. That's the way it is. All of a sudden, the company will just erupt. But there was, 5-10 years of work that took place in order to put the chessboard in place. And that leads directly into the next question about how the technology works. What I'll do is I'll bring up an image here.
So every lithium-ion battery has 5 main layers plus an electrolyte. So it's aluminum and copper foils, which are the current collectors that bring the electricity in and out of the battery, the anode and cathode materials that hold the lithium, and then a plastic membrane in between them. The whole thing is then flooded with an electrolyte. The membrane allows the lithium to go back and forth, but keeps the electrodes from touching. Every lithium-ion battery fire starts when something punctures that membrane. The energy flows into that spot, generates heat. The heat causes that plastic membrane to shrink, which opens up a bigger hole with more energy flowing and then more heat and more energy flowing, and that's the spark that lights the battery on fire. So we're doing two things different. The first is we replace that plastic membrane with a nanofiber nonwoven based separator. It's a paper. We start with textile grade fibers. We fibrillate them down to nanofibers, add in some other materials, and then feed that into a paper machine to make a thin uniform sheet. The beauty is that because it's a mixture, we can reinforce this with Kevlar nanofibers that are stable to 500 degrees Celsius. So it's never going to melt or shrink. It'll char a little, but it always retains its shape. The next thing we do is we replace those metal foils with metallized film. So think a party balloon or a potato chip bag. We have a thin layer of plastic film with just enough metal to run the battery, but not enough to support the intense current densities that would light it on fire. Now, when you get a damaged spot or a dendrite or something that causes that short circuit, the energy flows in, it generates heat. The separator will char but not melt or shrink, so it never gets worse. And then the current collector actually burns out like a fuse. The plastic pulls back, and you've got a dead spot in the middle of the lithium-ion battery with the rest of it continuing to function.
Are both the separator and the current collector technologies, are both of those required in order for the system to work?
Yeah, so every battery has both a separator and a current collector. You don't have to replace all of them with our material. And what we found, and this is some ongoing work with NASA that they are submitting to a very prestigious publication, I think Science, where they've shown that each time you add one of the Soteria components, it improves the safety of the battery, reduces the amount of energy that comes out if you do light it on fire. So if you throw it in a fire, it's going to reduce the amount of energy that comes out. And so each time you add a single component, it gets more and more safe. For small batteries, you probably don't need all three. For the big cells they're using to power things like electric aircrafts and the bigger vehicles, you might need all three of them.
Now, how is this produced? Because, for instance, if you look at a regular current collector and a battery, there's a limit to how thin you can make that current collector because it starts developing pinholes and surface imperfections, and they tear very easily because they're as thin as aluminum foil and they're moving at meters a second. And what you've done is you've actually, in that same space or even a smaller space, you've managed to put 3 different layers. How does that work?
Yeah, so we start with a polymer film, and the polymer films are, believe it or not, available down as thin as less than a micron. And because polymer is like chewing gum, you can just stretch it and make it thinner. And so that's what they do, is they cast it and then they stretch it and make it thinner. And then we take that polymer film and we run it through a vacuum physical vapor deposition. So essentially the polymer film will go across a molten pool or over the top of a molten pool of metal. The vapor will deposit onto the polymer film, and then it moves on. And this is how food packaging, potato chip bags, party balloons, all metallized film is made this way. We've piggybacked on that process. Now the trick for us is we want to use less polymer, more metal, and so we're pushing the limits of what you can do there. Actually, Applied Materials and Bueller, 2 equipment companies, are advancing kind of the state-of-the-art technology to do what we're asking. And that's the beauty of the consortium. We're working with the best in the world to improve our own processes. And they're doing the heavy lifting, and they're the best in the world, right? Far better than we are at what they're doing.
The way that I found out about Soteria was actually an article in Converting Quarterly, which is a publication that's dedicated to creating films that go into products and things like that. So that explains now why this would have been included in that publication.
Yep.
What would the impacts to cost and performance at the cell level be? Would this add cost to the battery? And how would that impact performance at the cell level in terms of energy density?
Yeah, so a couple of things there. The first is the safety performance obviously gets better. The weight goes down because the plastic's lighter than the metal. And so the energy density on a weight basis goes up by between 10 and 20% just because we've removed the metal. The other thing, the beauty is, because that metal is expensive and we can make 10 batteries with the same amount of metal that it takes to make 1 battery today, the cost actually will go down in large volumes also. And this process has been used since the 1950s for food packaging. So it's not a new process. It's just never been used in batteries before. So the first one's always going to cost a lot. In large volumes, the weight goes down, the energy density goes up, the electrical performance remains basically the same, and the cost should go down.
As I'm listening to this, it seems too good to be true, because it seems like one of those things that's a global optimization that improves every area, and there doesn't seem to be any real drawbacks. So what sort of challenges are you facing? What are the next steps? And why haven't we seen this in products yet? Or when should we expect to see it in products?
Yeah, I was going to say, the only reason I haven't seen it in products yet is because we only thought of it a couple of years ago, and it takes a few years to get it fully baked. We got first large quantities, so ton quantities of high quality material at the end of last year and the beginning of this year. From that point to full commercial batteries is probably 2 years. So we're targeting first commercialization at the end of next year, full commercialization in 2022, and probably in handheld devices first. And that's why, to answer your question, we actually promote this as, you know, improved safety and no compromises. And the no compromises captures the reduction in weight, the reduction in cost, and the fact that it's a drop-in to every lithium-ion battery chemistry, every lithium-ion battery architecture, and every form factor. So, and every manufacturing plant. So a lot of solid-state batteries seem really interesting, but you got to build a whole new factory to build the first battery, right? That's hard.
And that's probably a point worth dwelling on, because one of the benefits of solid state that's touted is the fact that it's more safe and non-flammable. But what you're actually able to do here is take the existing chemistry and make it safe without any impacts to the rest of the battery. And what I'll do is I'll include some video of the puncture test that you provided me to show a nail going right through this, and the battery does nothing, whereas a typical lithium-ion battery just goes up in flames.
Yeah. No, that's good. I'll tell a short story here. I don't know whether you want to include it or not, but in 2017, I bought a couple of Galaxy Note 7s for obvious reasons, and I took them apart. First, I drained it down till the phone said the battery was dead, and I took them apart. And then I went with this dead battery in the phone, I went with just a thin kind of a screwdriver, and I tried to just gently pry the battery out. Blew up in my face. Literally flames everywhere. I was wearing gloves, thank goodness, but I ran the thing to the back door and threw it out in the yard. And the only way to get that, and this was a dead battery, the only way to get it to where I could actually get the battery out and disassemble it and inspect it was to, once I'd opened the phone, take some leads to a resistor and stick them into the leads to the battery and drain it down to 0 volts. So I let it sit there for a couple hours just draining. And at 0 volts, I could lift the battery out without it blowing up in my face. But at dead battery volts, I couldn't.
I'll definitely keep that, and everybody always appreciates a mad scientist story. Yeah. And I've noticed well, I noticed that some of the videos that you posted on YouTube, it looked like you did it at home on your kitchen counter where you put a lighter up to one of the separators. So I like that. I can appreciate that.
Yeah, good.
Now, generally with these, when I'm conducting these interviews, there's a number of things that come up in my mind as to what could block or prevent a technology from being implemented. And that's where a lot of the conversation derives from. But you've covered all the concerns I have here. It seems to be an improvement in every area. It's manufactured using standard manufacturing equipment and well understood processes. And a large group of companies are going to be able to access and utilize this technology. So I guess my last question would be, is there any manufacturers that have signed agreements with you for licensing to start putting this in your products?
So we've signed one license for the separator. And the way we license the material manufacturers, and then everybody else just sees them as a supplier. So we have a very kind of a small segment of the value chain that we're inserting ourselves into and really inserting some new companies into, but big companies. And everybody else just sees them as a supplier. So these are generally tier 2 automotive suppliers, which is where they fit here. So people are comfortable with them. We've signed one license. We have 9 other consortium members who are manufacturers of these materials who are implementing it on their manufacturing equipment, scaling it up. They've gotten, several of them have produced, full ton quantity rolls, and we expect them to be taking licenses pretty soon. So there's a process that we're going through. Our goal is to have at least 2 manufacturers of each material fully licensed by the end of next year. And those guys are already in the consortium, already doing the work. So,
what's the biggest challenge that your team has had to overcome to develop these technologies?
Yeah, so my co-founder and I, Carl Hu, when we founded the company to commercialize the current collector and start the consortium, we didn't know how to connect different layers of the current collector together, because traditionally in lithium-ion batteries, you have a stack of metal tabs, you weld those together, they weld very nicely, and it's all metal-to-metal connections. We had something that was 90% plastic and didn't conduct from one side to the other like the metal foils do. And so we didn't know how to weld it. So we literally went to the whiteboard, drew a full array of different ways to make these connections. And then we went and bought a welder, and within weeks, Carl had figured out how to weld and push the plastic out of the way and extrude the metal layers down through the others. And we've now welded 32 layers to a single tab with 32 layers of metal all connected together. Well, 64 layers of metal all connected together, and all the plastic pushed out of the way. And all that's with standard ultrasonic welding. And that was, every bit of that was Carl just tinkering in the lab and making it work.
Now, I've heard about ultrasonic welding. What is ultrasonic welding, and how does it work?
Yeah, so basically ultrasonic welding, you take your stack of materials or your 2 materials and you put 2 horns on them. One of them is an anvil, it holds still. The other one wiggles at ultrasonic frequencies, and it doesn't create enough heat to melt the metal and make it glue together. Instead, it wiggles the metal at the interface just enough to scrape off all the oxides and get the metal molecules, the metal atoms, in intimate contact, and it makes a full contact. And that's what normally happens. What we had to do was generate enough heat with these anvils, push the plastic out of the way as we're pushing the metal through the plastic, and then weld at the other end. And we had no idea that was going to work until we did it. And even after Carl did it, I was still kind of like, okay, you got to really show me that.
Oh yeah, I'm struggling to understand it here. I think I'm going to have to rewatch this a couple of times to fully understand it.
I'll send you a picture you can use. We got a nice cross of everything just going right through.
That'd be great. And what it reminds me of the ultrasonic welding, it's kind of a micro version of friction welding.
Yeah, it is. It's very much like friction welding. It's just at ultrasonic frequencies.
All right. Another question people might be interested in, they're going to want to know when this product could potentially be in a Tesla vehicle.
Yeah, so I can't say anything specific about any specific company, but let me talk about automotive companies in general, and then I'll say my impression is Tesla moves faster than anybody. We've got several of the big-name automotive companies who are watching our technology closely, several who have the materials and are doing the development themselves. The battery development cycle for electric vehicles is 3 to 5 years. Tesla would probably be at the front end of that. The other guys that we know would be at the tail end of that. And we are just starting that cycle with several different companies. So again, not saying anything about anybody in particular, but we've started that process now with 5 or 6 different companies. And 3 to 5 years from now, we should be in electric vehicles. And that's hundreds of millions of square meters of material being produced. That's a factory floor full of machines making this material. So we've got some growing up to do during those 3 to 5 years also.
Do you expect to make the company public at any point?
That's my hope. I think Soteria does well as a standalone company. So most of the time with a private company or a startup like this, you're either going to sell to a strategic or stay standalone. And I think it does well as a standalone company. And my vision is just like, so nobody knows that we're now on Bluetooth 5.0, right? There's been many different versions of Bluetooth. And I think that there's a place in the battery industry for safety, for us to cherry pick the best technologies out of Stanford, MIT, Tsinghua, Fraunhofer, the national labs across the world, and make them available, do the hard work of figuring out which ones are the good ones and scaling them up, and then make them available to the rest of the world. And for safety, everybody understands that if the battery industry gets safer, that helps everybody. And so there's a willingness to share. For safety, compete on everything else. But for safety, let's make them all safe, because then everybody gets better. Because then you've got them in your living room, and you've got them in your daycare, and you've got them in your cars and in your aircraft and everywhere. So the whole industry gets better if we all get safer.
I love that thinking, and that's a great place to end this.
Yeah, good.
Thanks for your time, and I'll be keeping a close eye on Soteria. I'm really excited about the technology, and I'm surprised that I haven't heard about it anyplace else. I was lucky enough to find that article in Converting Quarterly.
Yeah. Thanks for finding it. We're working hard at getting it right now, and bringing in the right companies to do it. And we're not doing a very good job of getting the word out. That's on me.
Well, it looks like you're laser focused on delivering, and I appreciate that in a company that delivers rather than ringing its own bell.
Yeah, I appreciate it. And I look forward to seeing the video. So thank you.
Sure thing.
Yeah.
Have a good day.
Okay. You have a good day.